Soundness. The rules of natural deduction are not arbitrary. They are chosen to reflect the rules that we use when we make inferences in science and everyday life. The rules for the quantifiers are the way they are because that is how we use quantifiers. That is how we understand them. One may be convinced of this by merely looking at the rules. However, this can also be proved, and the result is called the soundness theorem. But how can we possibly prove that the rules reflect our everyday use of language? Well, we can prove it to a certain degree of accuracy. This accuracy is provided by the concept of satisfaction of a formula in a model. We can prove that what we can deduce from a formula A by means of natural deduction is satisfied in every model by every assignment that satisfies A in the model. So if our concept S satisfies A and M of satisfaction reflects faithfully our concept of truth, then the soundness theorem will show that natural deduction preserves truth and is therefore sound. The main application of the soundness theorem comes in a roundabout way. We can use it to show that certain deductions are impossible. Let us take a simple example. It is intuitively obvious that we cannot deduce for all x p0 of x from there is an x such that p0 of x. But how to prove it conclusively? When we have the soundness theorem in our hands, we can simply construct a model in which there is an x, p0 of x is true, but for all x, p0 of x is false. This does it. Soundness. Soundness of natural deduction in predicate logic means that deductions respect truth in the following sense. If A can be derived from the assumptions B1 up to Bn, and the assignment S satisfies B1 up to Bn in a structure M, then S also satisfies A in M. The derivability of A from B1 down to Bn means the existence of a natural deduction that has B1 down to Bn as the assumptions and A as the conclusion. So we have to look at all such deductions. Deductions are built up from individual steps which are rules, rules for connectives, and quantifiers. The idea now is that we show that truth, or rather satisfaction by an assignment in a model, is preserved at each individual step of the deduction. Then truth, or satisfaction, flows from the assumptions step by step to the conclusion. This is just like inductive proofs in arithmetic. If we know that f of 0 is even, and then go on to show for all n that if f of n is even, then f of n plus 1 is even, then we know that f of 100 is even, because we can, in our mind, start from the evenness of f of 0 and proceed step by step all the way to f of 100, and then conclude that also f of 100 is even. So we prove the claim: if A has a natural deduction from B1 down to Bn, and S satisfies B1 down to Bn in a structure M, then S also satisfies A in M. The proof is by induction on the structure of a natural deduction. The deductions consist of steps, which are applications of the rules of natural deduction. We proceed from simpler deductions to more complex ones. We show that the conclusions of such applications of the rules are all satisfied by S in M. We go through all the rules, and in each case assume that the assumptions of the rule are already satisfied by S in M, and show that the conclusion is likewise satisfied by S in M. Many of the steps are completely trivial and may have been discussed already when we motivated the rules, but this should not deter us. The point of this proof is the combined effect of all the small steps. Individual steps may be trivial, but the overall conclusion is not. The shortest possible deduction has some formulas B1 down to Bn as assumptions, and one of them, say Bi, as the conclusion. The claim that any assignment S that satisfies B1 down to Bn also satisfies Bi is automatically true. We consider now a deduction with the assumptions B1 down to Bn and make the induction hypothesis. All smaller deductions satisfy the claim that any assignment S that satisfies the assumptions of the deduction also satisfies the conclusion. What does smaller deduction mean? We rely on the intuitive concept that a smaller deduction has fewer applications of the rules.
Conjunction. Let's see what happens to the conjunction introduction rule in the induction. So we will check whether the condition that if an assignment satisfies the assumptions of the rule, then it satisfies the conclusion of the rule, whether this is preserved by the conjunction introduction rule. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn. We assume S satisfies A and S satisfies B, and we have to show that then S satisfies A conjunction B, but this is entirely trivial. Then the conjunction elimination rules. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn. We assume S satisfies in M A and B, and we show that then S satisfies in M A and S satisfies in M B, but this is again entirely trivial. Disjunction rules. First, the disjunction introduction rule. There are two. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn, and let's assume S also satisfies in M A. We want to show that then S satisfies A or B, but this is trivial. Also, if we assume S satisfies B in M, then again trivially S satisfies A or B. Now comes a more interesting case, namely the disjunction elimination rule, because here we have temporary assumptions which make this case a bit more exciting. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn. Moreover, we assume S satisfies A or B. Let's look at the derivations of C from the temporary assumption A and of C from the temporary assumption B. These are derivations that are shorter than the entire derivation that we are now looking at. Whatever shorter means, it is obvious that these deductions are shorter than the whole original derivation of which these are parts. So, by induction hypothesis, the derivation of C from A as well as the derivation of C from B are sound. That is, if S prime is any assignment that satisfies in M the assumptions B1 to Bn, and moreover S prime satisfies A, then S prime satisfies C. And if S prime satisfies B, then also S prime satisfies C, whatever S prime is. We show that now S satisfies C. Well, we know that S satisfies A or B in M. So S satisfies either A in M or B. Mind you, we don't know which. But anyway, one of them holds. But in both cases, by induction hypothesis, we get that S satisfies C. So, whichever case it is, A or B, we can conclude that S satisfies C.